You are now well on your way to becoming an expert coder and elite computer hacker. This past week in Foundations of Algorithms, we learned about control structures, if, else if, and else, along with switch statements. We covered order of operations and a whole bunch of different operators, along with all their traps and tricks. We also covered loops, for loops, and while loops, with a brief mention of do-while loops. We're setting ourselves up for an exciting next week. Functions, pointers, and arrays are on the table, and pretty soon, control of the entire world will be at your fingertips. I hope you're looking forward to the next week of Foundations of Algorithms.
In front of you today is Katherine Johnson. She was one of the first black computer scientists to work at NASA. When she was first hired, she was called a computer. But in the sense in which she was called a computer is not the same that you might think of your laptops in front of you today. Her job was to perform complex analytical calculations, including the trajectories of various different space missions. Later in her career, once digital computers started to permeate the workspace, Katherine Johnson eventually took command of those and helped her colleagues to use computers to plot the trajectories of different manned spaceflights, including the famous Apollo 11, which resulted in man's first step on the moon. So what is a function? A function is a basic mechanism to control input and output on the computer. Let's say we have two inputs. This might produce a single output from the function. In C, we only are allowed to have a single output from a function. A function might then be chained to a subsequent function. Let's call this function g of a, because it takes the output, the single output of the prior function. And then this can lead to more and more different functions. In the C programming language, we always start with a function that you're now familiar with, the main function. This takes two inputs that we'll explore as we learn about their types, argc and argv. We already know how to understand the type for argc. It's an int. Argv's type is a little more complicated. It's a way of representing an array of strings, arrays which we will cover at the start of next week. So for example, let the function signature of our function output a character. This is the return type and the first thing that you write when defining a function. Next comes the function name, that's the letter F over there. Our open parens specify that we're beginning our argument list, and the two arguments to our function are an int a and a float b. Once you've added your function definition, you open a curly brace to signify that you're now going to start writing the body of the function, the contents of the function. This is where you do stuff, and when you're finished doing stuff in your function definition, you close it off with a paren. This is identical to the main function that you've been using already, but it helps when we're writing larger programs to abstract out the different tasks and the different chunks of our programs into smaller functions. In fact, this is one of the hallmarks of good code style. Have you broken up the program adequately into a number of small different steps, such that no function in your program is doing too much work? Why do we do this? It helps us to manage the complexity of the program, both from an efficiency sense, but also from a logistical sense and a code maintenance perspective. When it comes to writing larger programs and maintaining them, that might be not just one file, but might be hundreds of files and tens of thousands of lines of code, this process of abstraction is really critical. More importantly, we need to learn some of the terminology surrounding functions. The first thing that one ought to know is what we call the function that runs the other function. So let's say you're inside main and you want to run a subroutine that calculates the sign of a number. The main function is the caller of the sign function. It's the function that asks for it to run. The subroutine we're going to call the callee. Too many calls in one sentence. And we call the process of running a function, of executing a function within another function, we call that calling a function. So we have calling, callee, and caller, all important terminology. Knowing that will make the rest of our process a lot easier. The next key fact is how to get stuff out of the function. This is what we use a return value and a return statement for. The return word, if you see it at any point in a function, know that the function terminates whenever it reaches that statement. But not only does it terminate, the variable or the value that's written subsequent to the word return is given back to the caller. And we'll see how this is structured in a real program momentarily. So our caller gives input in the form of arguments, that's the word for the inputs, to the callee, and the callee returns a value on termination. When a function finishes running, the program immediately resumes running back at the point at which it was originally called. So if you have a function of 10 lines, that's your main function, that goes from lines 1 to 10, and then lines 15 to 20 is the sign function. If the sign function is called on line 5 in the C program, in the main function, when the sign function finishes, we're going to go back and resume at the end of line, finish processing line 5, and then move on to line 6. So the program has jumped from line 5 temporarily to line 15, and then when it finishes that function, when that function returns, we go back up, finish off line 5, and then continue processing on where we left off. Whenever a function terminates, all its memory, all the variables associated with that function get destroyed. They're no longer accessible. Now, as some of you might ask, well, what happens to that memory? Where do they go? The memory does not get zeroed. Those variables are still there inside the computer, but your compiler and your programming language will no longer let you access them. This is important to know, particularly if you're doing something that's really security focused, because if the function terminates and you're relying on that to remove your top secret variable, you should know that you actually have to zero that variable first to ensure that it actually disappears. There is one exception to this rule, though, and that is static variables. These are looks like we're a little behind. Yeah, there we are. The exception is static variables. Static variables do not get destroyed when the function returns. In fact, they stay in the program's memory for the next time the function is called. What this means is you can have the function remember what happened last time the function was run. This is quite a flexible and creative tool, but with flexibility comes the potential to abuse it. In this class, we'll highlight a few key ways for you to use it, and also a few ways for you to misuse it. So there's another trap. Either a function's signature or the function itself must appear in your C programming file before you actually use it. Why is this? Say I was to have a function named complex computation, and inside my main function, I declare some variables, int a, int b, and then my next line is complex computation with the arguments of a and b. How does the compiler know what complex computation is? Well, in some languages, what your compiler will do before trying to generate the code for that program is it will look through your entire program and check to see if you have made complex computation anywhere in your file. The C compiler follows a slightly different set of rules. During the main compilation phase, it's only going to recognize the function if it's already seen it earlier. Now, one way of it having seen it earlier can be in header files, so those little include statements up the top. That's one way of letting the compiler know what a function might be before you try and use it. Examples of this would be printf and scanf. In order to use printf and scanf, you don't have to write printf and scanf and explain to the compiler what it is early on. Instead, use the header file, this include directive that we have at the top of our files. However, when writing your own functions, at least when you're getting started, you won't be using header files, and so you need to tell the compiler what these functions are. So the two ways of doing it: number one, just write your whole function earlier in the file. That is one easy way of doing it, but it can get messy fast because it requires you to figure out ahead of time which functions are going to use which other functions and remember the order, and also order them such that it works out perfectly. And this won't even always be possible. So the C language provides us with a workaround. This is the use of function prototypes. A prototype essentially tells the compiler ahead of time that somewhere ahead of you, there is going to be this function, and this is what the function looks like. And when I say looks like, what I mean is the type of the function, the return type of the function, the name of the function, and the arguments of the function. And to conclude a function prototype, instead of writing the function body next, you simply end it with a semicolon. Let's take a look at how we might write one of these. We've got an error. Implicit declaration, complex stuff is invalid in C99. That's telling me that we have implicitly told the compiler what complex stuff is without doing it properly. It's complaining because we're asking the compiler to imply the type and imply the structure of complex stuff. What we should have done instead is something like this. Oh. Okay. Now we have another error. Undefined symbols for architecture, x86, x64, complex stuff reference, blah, blah, blah. Symbols not found. Linker command failed. What does this error mean? When you get an error like this, what it means is that there is a function definition somewhere, there's a prototype that exists, but when the compiler runs through trying to match the prototype, when the linker, and we'll get to that in a second, when the linker goes through and tries to match up the prototype of the function with the actual function, it can't find it. Now, what is this linker? I thought you were talking about compiler. You even said that yourself. Well, part of the compilation process is what we call linking. This involves the matching up of different functions from their declarations to their actual code. When we talk about libraries, you'll see that when we use code from other places, we need to have some way for our C compiler to collect all these different pieces from across the computer, code that you've written, code that people who built Linux have written, code that you wanted to borrow from someone else, and mash them all together into a single executable. So when the compiler's finished running, it automatically runs a linker program that jams all this code together into the executable, or if it doesn't jam it, at least tells your operating system where it can find these other pieces of code. So now that we understand our error, we can go back and hopefully correct it. Now I'm going to make this the most complicated function I can think of. I think that's complicated enough. And to make my program one bit more complicated, I'm going to print out the results so we can actually see what we've done. Give it a run. Ta-da! Our very first function. Another thing to note while we're on this point is that here I've used the variable name a consistently. This is in fact a little confusing because the variable a inside the function is not the variable a inside main. This is an effect of what we call scope, the fact that variables belong to one part of the program or another. Let's explore this concept a little more today before covering it in greater detail later. So let's say I change this to b. Inside this function, there is now a variable called b. Why is there? Well, because I've told the compiler that whatever input is given to the function, call that first input b. Whatever it was called in the place it was coming from, we don't care. Now that we're inside complex stuff, whatever complex stuff has received will be called b. If we go back to the top of our program, our a hasn't changed here. Well, now our a hasn't changed inside the main function. In fact, you don't even need to tell the prototype the name of the variable. It's good practice to do so, and I don't recommend getting rid of it, but this will work. See, it still prints out the same thing. If I were to take the return value of the function, I could also call it something different. These are all different variables, which is a byproduct of the language having scope, which actually makes your life easier because you don't need to remember all throughout the program the names of every variable that you've used in any different point and avoid collision and make sure there are different names for all of them. This is actually a feature, not a bug. It makes programming much, much easier because within a given function, you only have to worry about the inputs of the function, the outputs of the function, and the transformations that you do within. This gives us the ability to, yeah, Xinjiang.
So variables declared as parameter is also a local variable?
Okay, let's test. There we go.
I just want to ask if variables declared as parameter are they also local variables?
Yeah. So the question is, if I give a function an argument, are these the same as local variables, variables that you initialize or declare within a function itself? Now, they are almost the same in that they live in the same place in the computer's memory, and they get destroyed in the same way. The only difference is how they're initialized. Because when the compiler goes through and constructs your chain of going from one function to the other, the things it has to do to set that up look a little different from when you declare a variable within a function itself. So very, very similar, and from your perspective, there's going to be almost no difference. You can use them just like normal variables. This gives us the ability to start talking about libraries, reusing code from other places that are not just within your own code. Now, this is important because C doesn't come with batteries built in. Unlike Python, with Python, there are special functions you can call to download stuff from the internet. There are functions you can call to reverse the order of things, to sort things. C is just a language without coming built in with the ability to do all of that stuff. That would make it a pretty unfortunate language, as any time we wanted to do any of these very, very common things, we'd have a lot of work cut out for ourselves. So what's our solution? Thankfully, C has been around since the 70s, and so plenty of other people have written this code already for us. And even better than that, they've packaged it up into things called libraries. These are collections of both the C code and the headers that help our compiler find the code and tell the compiler about the existence of the code that we can include in our programs. This is equivalent to Python's import statements that some of you might have seen. There are lots of different ways to build different sorts of libraries by telling your compiler how to do it and how to structure your code so that you could include it. But for the most part, the goal for us is going to be incorporating other people's code through the use of include statements. Now, This would all be great if the computer knew where to find the files that our include statement was talking about. And some of the time it does. For the very, very most frequently used header files, they come packaged with the compiler when you download your compiler, and they're part of something called libc, the library that's attached to C kind of as a default that every compiler and operating system tends to come with. Now, if you want to compile without libc and operate totally on your own, you can. It's a little complex and I don't advise it, but the point is C gives you the power to shoot yourself in the foot. Now, what if we want to use something that is common, but perhaps not quite so common? Well, what we have to do then is tell our linker where to find the library files that contain the header files and the C code. Luckily, the linker syntax is generally quite simple. When we compile our file, we add something to the end of the command line. We add a flag -L and then type the name of the library that we're trying to add. The first library that all of you are going to encounter is libmath. This includes things like sine and cosine, which aren't obviously super necessary to be part of the language core because there are a whole lot of different methods for calculating sine and cosine. It's not the most frequently used function, but it still seems something reasonable to make easily available. And so these are made easily available through libmath. When on your operating system you want to include a new library, you have to first learn the name of the package to download the library onto computer, and then the right flag to add to the compiler, the right include to put at the type of your program, to put at the top of your program, and how to use the actual functions inside the library. So you might also look at the library's man pages. Seems like a lot of work, but it's worth the gain. Let's check this one out too. I'm going to scroll out a little and open it from here, because then we might get nice large font size. Maybe. So just like in past lectures, we have our demo programs all set up on the side, and now I can avoid bending over for a little. So we are now on lecture 4, and we have some code. Here is our example program to use libmath. We're going to show a bunch of different functions: sine, log, absolute value, square root, certain constants that are hash defined inside the library. We have pi and root 2 already defined for us, and we are going to apply that to a variable provided by the user. Note at the top here, we use an include, math.h. This is the header file attached to libmath. If you include this header, you will then have access to all of libmath's functions, assuming that you remember to tell the compiler that it has to tell the linker to include libmath. So let's actually do that. Yeah, so this is actually what I suspected might happen. And I'll tell you what's going on here in a minute. You'll notice that I didn't actually end up passing the linker flag. I didn't do the /L math. And this is a little bit surprising because I just spent all this time telling you about how it's necessary. It turns out that some libraries are so fundamental and so common that even if they're not in libc, the compiler automatically engages its intelligence and includes those libraries for you, and libmath is one of those. So this demo, which would have been an interesting challenge back in the 90s, now works on its own. And I had a suspicion that that would be the case, which is why we didn't try it the first time. So now let's put in our library flag, and it doesn't even work anymore. What about with GCC? Perhaps libmath is now built into Clang. That's also totally possible. Oh, that's true. Yeah, LM, sorry, not -lmath. Thank you on that one, Liam. But you can see that both of the compilers are updated in recent versions to incorporate libmath, and there are probably even some other libraries that are in there as well that we can look up after, and maybe I'll make an ed post about. So along with all of you, you can see that the language, because the language evolves, I have to learn as well, just as much as you guys, about the evolutions and changes to the C programming language. Some of these things, as I discover throughout the semester because of the new version of C coming out next year, I'll post for you on ed so that you can see and find out about these new features as I'm learning them too. So let's clear our terminal there. And like with past lectures, while we are learning new C concepts, we're going to be doing a lot of demos. So let's do a few more of those. Last week, we looked at generating a table for interest rates that could be interesting for doing our little financial calculations if any of you are interested in personal finance. Going on with more of this theme, some of you might be interested in actually figuring out how to set up a savings plan more consistently and doing your own mathematical modeling for what your personal finances might look like. Well, for this end, we have a fancy program that we have already built for you that will help you with your savings plan, and you can tweak and modify as you wish. In this case, the saving plan sets an amount that you're going to be saving per however long, the amount of years that we should project into the future, and the annual rate of return. The goal here is to illustrate the use of functions in some broader context. Ooh. In our main function, we've separated out the process of receiving input from the user from the process of actually carrying out our calculations. This is a key exemplar of the process of abstraction. Conceptually, reading things in and spitting them out and computing them are each very different tasks. And so when writing our program, we want to split these out into their own functions. Because our program is relatively simple, we can be comfortable doing the main input and output inside main and leaving the calculations to its own function. Here we have a standard set of scanfs and printfs. We're reading in an integer for the number of years and two long floats, or doubles, for the rate, because these are floating point numbers, and the amount that we are saving each month. We're going to run the savings plan a series of times. Each time, we're going to provide it with the respective arguments that suit the year we're up to. So let's give it a run and see what happens, and then we can go back to the code. Pull this up so we can see it a little better. Enter number of years. Let's do 4 years, an annual rate of, what should I pick for the annual rate? 2. Monthly amount, how much do you guys think you can save on a month? If you don't eat any avocado toast for a whole week, you think you'd save 50 cents on avocado? You guys are eating very cheap avocado toast. So let's say my avocado toast budget, like many of you, is $700 a month, enough for a house deposit. At 1% per year, we would have $34,000. That's enough for potentially a small home 300 kilometers off the coast of Adelaide. At 2% per year, we would make almost $35,000, and at 3% per year, we would make over $35,000. So getting us maybe 80 kilometers off the coast of Adelaide for our first avocado toast home. So there's still a long way to go. Let's see how we did this. Each time when we called the function, we looked at what would happen if the rate changed from the value that we had contributed to the program initially. What would happen if the rate was we said 2%. So what would happen if the rate was 1%? What if the rate isn't as good as we thought? And then what would happen if the rate was 1% better than what we thought over here? Abstracting out the computations into the function allowed us to run it in different ways very, very efficiently without copying that whole computation code, which you saw above, multiple times over. In this way, abstraction is powerful not only because it helps us conceptually to separate things, but because it allows us to reuse code in different ways in different scenarios. Let's take a look at the actual computational code and see if there's anything interesting there. This looks rather similar to our code that we had previously to generate the table based on interest rates. We have a for loop that iteratively goes and adds the interest over the period of years. The big difference here is that in this case, we are taking in 3 inputs. Our inputs are the amount contributed, the annual rate for the function, not for the overall program, not for main, and the number of years. And each of these could differ from the variables in main. As an example, let's say that I want to project out what happens in 10 years if the interest rate is better than I thought it was, but for 1 and 2 years, I want it to stay the same. And I'm going to comment out this statement so the program doesn't lie to us. What's it unhappy about? Oh, that's on a separate line. And I've still been bad. Who can tell me what I've done wrong here? Why is the compiler unhappy? Need to scroll up to give you more of the error for that to work. Liam, do you want to run the microphone over to whoever answers? Okay, where is Grace? Grace, put up your hand. Okay.
I think because 10 is an integer and you put the format specifier for double or float.
Exactly. So what has the compiler done for us? Is our program going to run?
No, I think, especially because you put the decimal 0, it just warns you that it can't do a decimal on an integer.
So keep the microphone for a second, and we're going to see what happens. Well, the program started at least. Let's see what kind of an answer we get. What did I say? $700. Well, the program did run. Do you have an idea why we might have been able to ignore that warning?
I think because, I don't know what the correct term for it is, but I think it's casting, so like because float is higher, or like, I don't know how to explain, but I think you get it.
Exactly. What's going on here is the compiler is guessing at what we want. It's guessing that we want it to do type promotion, to automatically convert the constant value that we've put in there, what was it, 10? Yeah, it's converting the 10 that we put in there to 10.0. Because from the compiler's perspective, it can understand that both of these are numbers. It's a little cleverer than we are, and so we'll do this automatically. However, it still provides us a warning to let us know that something fishy is going on and we might want to check it. Remember is prime from our last lecture. Now, if you've been paying attention to Ed, you will have noticed that I made a bit of a silly mistake in the last lecture. I told you that the function was inefficient, and that was true, but I also told you that it ran in root n time, which is pretty fast. So what's going on there? Well, the function is slow, and it does kind of run in root n time. It performs that loop, root n times, but we forgot to ask how fast are those operations inside the loop. They look like normal mathematical operations. It was the modulo clock arithmetic thing, which on numbers we presume is instant. When we're counting how many times a computer is doing something, for the purposes of figuring out the runtime, we just assume that arithmetic is fast. Well, this is true on a small scale when we're dealing with small numbers that the computer is familiar with. But if we're trying to run this algorithm on cryptographically large numbers, it's not actually true that arithmetic is constant time. If you figure out when you're doing multiplication, when you're doing your multiplying two 5-digit numbers together or doing long division, there's a process that you go through to figure out how to actually get the answer. And that process isn't just instant. It's not looking at the two numbers and then figuring out the answer just because. There is a process that you have to go through to do the computation. Likewise, inside the computer, there is circuitry that very efficiently deals with this for simple numbers, but the circuitry doesn't exist for arbitrarily large numbers, for numbers that have larger bit lengths, particularly when we want to deal with numbers that go beyond 32 or 64 bits. And so, the right question to be asking for doing computations on really large numbers is not the efficiency in terms of the number of arithmetic operations we do, but the efficiency in terms of how large our input is, which is computed in the form of the length in bits of our number. So is prime does run in root n, but if we calculate the complexity in terms of the bits, the size of the numbers that we're entering, it suddenly becomes exponential. And if I'm remembering, I don't remember the complexity off the top of my head, you can put, it's on Ed. So now that we've tackled that, let's go back to our isPrimeFunc and see if we can make it even slower and even more complex. So instead of just checking if a number is prime, remember that's what isPrime did, we now want to try and find primes. For our Diffie-Hellman key exchange, the little fun bit at the end of last lecture, for the cryptography, we actually need to have a really, really large prime ahead of time that Alice and Bob can use for this computation. And how are we going to get a prime number? Well, it would be really inefficient to just guess random numbers because primes aren't that common. Instead, what we could do is just go through the list of numbers one by one and check if they are prime, running isPrime on each of those numbers. Now, this is also going to be very, very inefficient. I don't have the complexity in front of me, but needless to say, it is not small, and there are prizes available, like many of the other problems we've talked about in class, for finding a more efficient way to do this. Going to the structure of the program, here we have our isPrime over here. This is almost identical to what we had before, only now the function takes in a parameter n and returns 1 if it is a prime number and returns 0 if it's not a prime number. Also, we have a special case over here. If n is less than 2, we know that it's not a prime number. One of the nifty features of working with functions is if you're using an integrated development editor, such as VS Code, one of these fancy text editing programs, you can click on the side of a function and hide it to make our view a little more efficient. This reveals to us another function down here, nextPrime. This is going in a loop, starting from the number after the input, and while it hasn't found a prime number, it just goes to the next number and then checks again. One interesting thing, one feature of this particular style is that you'll notice that the function itself is being used inside the condition of the while loop. What this means is by order of operations in C, when the while loop checks the condition, the function will run first, it will spit out the return value, then the not operator will be processed, so it'll flip the result of the output of the function, and then check if the flipped version is true or not. Remember, isPrime returns 1 if it is prime, so this will give us 1 if it's not prime, and 0 if it is prime. Because 1 if it's not prime is a true condition, this means that the loop will keep operating whenever isPrime is not true. So if isPrime is not true, that returns 0, 0 gets flipped to 1, 1 is true, and so the loop body executes. Now all we have left is looking at our main function, and it's a simple input and output. Enter a number, starting from that number, find the next prime. First check if the number you've entered is prime. If it's not prime, find the next prime and print it out. So let's give this one a run. Now I'm going to use my nice C flags. One thing that I should point out, actually, what I've been doing to help my typing faster is using a feature of the shell called tab completion. This will save you hours of time when you've started writing the start of a word and you want the compiler, and it should be obvious for the context for the shell to figure out what comes next. You can press tab, and the shell will finish the word for you. So I didn't need to type the rest of those letters, I just pressed tab. In some cases, you can also press double tab, and it'll give you a list of possible things that it thinks you might be interested in. In this case, I've customized my shell to give me this really nice styled list, but it'll work even if you haven't done that. Ooh. Now let's give it a run. That tip is probably the most useful thing you'll learn in this semester. Enter a number n. N is not a prime number. The next prime is 11. That ran pretty fast. Enter a number n. Let's try a pretty big number. Still running fast. And so we're not running into these problems of computational complexity as long as our numbers are relatively small. And now we've got integer overflow. And so it's gone looped all the way around and gone back to 2, because 2 would be the next prime number if you've accidentally gone into the negative numbers. One thing that I recommend you do at home is download this code and prevent this integer overflow bug from occurring at the place it does by converting the program to use unsigned integers instead of signed integers. And that'll give you a bit of a feel for the difference that that can make. And with that, I think we are out of time for today. Stay tuned for the next lecture. I've got some really exciting videos for you. And next week, even better, we have our first prop coming in. So get hyped for that. Thank you very much, everyone, and I will catch you tomorrow.